Hello, future scientists. I'm so excited to welcome you to a fascinating journey into the world of temperature, a concept that's all around us every single day, even if we don't always notice it. Today, we're diving into something you experience every day: temperature. Whether you're stepping outside on a chilly morning or feeling the warmth of the sun on your face, temperature is always at play, shaping our experiences and the world around us. Have you ever wondered why you shiver when it's cold or sweat when it's hot? That's your body reacting to changes in temperature. But how do we actually measure these changes? That's where the science of thermometry comes in. Thermometry is the science of measuring temperature. It means putting a number to how hot or cold something feels, so we can compare, record, and understand the world in a more precise way. And guess what? Measuring temperature isn't just for scientists in labs, it's something we all do. Bakers use thermometers to make sure their bread is perfect, doctors check our temperature to keep us healthy, and we all check the weather to decide what to wear. Understanding temperature helps us control our environment, like adjusting the thermostat at home or in the classroom, and keeps things running safely, from cooking food to running factories and even exploring space. There are so many different types of thermometers. Some are designed to measure the freezing cold of outer space, while others can handle the blazing heat of molten metal in a factory. Each one has a special job and a unique way of working. Throughout this chapter, you'll see how these amazing tools work and where you might find them in action, whether it's in a science lab, a busy kitchen, or even outside at a weather station. By the end, you'll understand the different temperature scales like Celsius and Kelvin. And you'll even learn about the coldest temperature possible, absolute zero, where all motion stops. Who knows? Maybe you'll be inspired to build your own thermometer at home or in class, and become a temperature detective yourself. So are you ready? Let's jump into the science of temperature together and discover the secrets behind the numbers that shape our world. Before we start measuring temperature and heat, let's take a moment to clarify some key terms that are essential for understanding how thermal energy works. These concepts form the foundation for everything we'll explore in this chapter, so it's important to get them straight from the beginning. First, let's talk about heat and temperature. Heat is the total energy contained in all the moving molecules of a substance. It's a measure of how much energy is being transferred from one object to another due to a difference in temperature. Temperature, on the other hand, is the average energy of those molecules. So, while heat depends on the number of molecules and their movement, temperature is just about how fast, on average, those molecules are moving. For example, imagine an enormous iceberg floating in the ocean. Even though it feels extremely cold to the touch and has a low temperature, it actually contains a huge amount of heat energy because it's so massive. In contrast, a tiny cup of hot coffee has a much higher temperature, but far less total heat because it's so small. This difference between heat and temperature is crucial in understanding thermal energy. Now, let's look at how we measure temperature. A thermometric property is any physical property of a material that changes in a predictable way with temperature. For example, the liquid inside a thermometer expands as it gets warmer, and the electrical resistance of a metal wire increases as its temperature rises. These changes allow us to create devices that can measure temperature accurately. By using these thermometric properties, scientists and engineers have developed a variety of thermometers, from traditional liquid and glass types to modern digital and infrared devices. Each type relies on a different property, but all are designed to give us reliable temperature readings. To ensure that everyone's thermometer gives the same reading for the same temperature, we use fixed points, specific well-defined temperatures like the freezing and boiling points of pure water. These fixed points serve as universal reference markers for calibrating thermometers. These fixed points act as anchors for our temperature scales, making sure that measurements are consistent and comparable no matter where or how they're taken. Without these anchors, it would be impossible to agree on what 0 degrees or 100 degrees actually means. But what about the lowest possible temperature? That's called absolute zero. At absolute zero, molecules have no kinetic energy left, they stop moving entirely. It's a theoretical limit that can never be reached in practice, but scientists have come incredibly close in laboratory conditions. On the Celsius scale, absolute zero is minus 273.15 degrees Celsius. On the Fahrenheit scale, it's minus 459.67 degrees Fahrenheit. These extremely low temperatures are far colder than anything we experience in daily life, but they're important for scientific research and understanding the limits of nature. The Kelvin scale is a special temperature scale used in science, and it starts at absolute zero. Unlike Celsius or Fahrenheit, the Kelvin scale doesn't use negative numbers. 0 Kelvin is the coldest possible temperature. This makes it especially useful for scientific calculations and understanding the true nature of thermal energy. With these key concepts in mind, we're ready to dive deeper into the fascinating world of heat and temperature. Have you ever wondered how we actually measure something as invisible as temperature? We use special scales to put a number on how hot or cold things are. These scales help us make sense of the world, from the weather outside to the science experiments in a lab. Let's explore the three main temperature scales you'll encounter: Celsius, Fahrenheit, and Kelvin. The Celsius scale is probably the most familiar to people around the world. It's based on the properties of water. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius, making it easy to remember and practical for everyday use. Most countries use Celsius for weather forecasts, cooking, and science. If you check the temperature in Europe, Asia, or Australia, you'll almost always see it in Celsius. Scientists also prefer Celsius because it's straightforward and fits well with the metric system. In the United States and a few other places, you'll see temperatures in Fahrenheit. On this scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. It might seem a bit odd, but it was designed to make everyday weather and body temperatures easy to read. The Fahrenheit scale was created in the early 1700s by Daniel Gabriel Fahrenheit. He based his numbers on a mix of early experiments, including the freezing point of salt water and the average human body temperature. That's why the numbers might seem unusual compared to Celsius. For scientific work, the Kelvin scale is essential. Unlike Celsius and Fahrenheit, Kelvin starts at absolute zero, the coldest possible temperature where all molecular motion stops. There are no negative numbers in Kelvin, which makes calculations in physics and chemistry much simpler. Converting Celsius to Kelvin is easy. Just add 273.15 to the Celsius temperature. This simple formula helps scientists compare temperatures in different systems without confusion. For example, 0 degrees Celsius is equal to 273.15 K, and 100 degrees Celsius is 373.15 K. This direct relationship makes Kelvin perfect for scientific research, especially when dealing with extreme temperatures. Kelvin is the official temperature scale for scientists worldwide. It's used in physics, chemistry, astronomy, and engineering whenever precise measurements are needed. Think of each temperature scale as a different language for describing how hot or cold something is. Whether you're reading a weather report, baking a cake, or conducting an experiment, knowing which scale to use is important. Celsius is simple and widely used, Fahrenheit is common in the US and a few other countries, and Kelvin is the universal language of science. Each has its own history and purpose. Understanding all three temperature scales helps you interpret temperatures anywhere in the world. Whether you're a student, a scientist, or just curious about the weather, knowing how to read these scales opens up a world of discovery. Science is cool, literally. Let's start with the constant volume gas thermometer, a super precise tool. It works by keeping a gas's volume constant and measuring how its pressure changes with temperature. As you heat the gas, pressure rises. This is measured with a manometer. These thermometers are used in labs to calibrate other thermometers. They're accurate and can measure from near absolute zero up to 600 degrees Celsius. Downsides? They're bulky, fragile, and slow to respond. Errors can come from leaks or not keeping the volume constant. Scientists use careful construction and corrections to get accurate readings. While not for everyday use, they set the standard for temperature measurement. Now, let's get electric. Resistance thermometers, or RTDs, use metals like platinum. As temperature rises, the metal's resistance increases in a predictable way. By measuring resistance, we get a precise temperature reading. RTDs are used in labs and industries for their accuracy and stability. They can measure from -200 degrees Celsius to 850 degrees Celsius, and are great for long-term monitoring. Downsides, they're pricier, need power, and respond a bit slowly. Lead wire resistance can cause errors, but engineers use special wiring to fix this. RTDs are a smart, reliable choice for accurate temperature measurement. Ever had your temperature taken without contact? That's an infrared thermometer. It detects invisible thermal radiation from objects and converts it into a temperature reading. Infrared thermometers are fast, safe, and can measure from a distance, even on moving or dangerous objects. Their accuracy depends on the object's surface and air conditions. Now, meet the thermocouple, a thermoelectric thermometer. It uses two different metals. When one end is hot and the other cold, a voltage is created. Thermocouples are rugged, cheap, and measure a huge range but aren't as precise as RTDs. They're everywhere, from engines to ovens. For extreme heat, like molten metal, we use optical pyrometers. These non-contact tools compare the brightness of a hot object to a glowing filament inside the device. You adjust the filament's brightness until it matches the object, then read the temperature. Optical pyrometers measure from about 600 degrees Celsius up to 3,000 degrees Celsius or more. They're vital in steelmaking and glass industries. Limitations? They only work on objects hot enough to glow, and readings can be subjective. Modern versions use electronic detectors for better accuracy. They let us safely measure the hottest places on Earth. You can be a scientist at home. Let's build a simple thermometer. You'll need a clear plastic bottle, water, rubbing alcohol, a straw, modeling clay, and food coloring. Mix equal parts water and alcohol in the bottle, add a drop of coloring, and insert the straw, not touching the bottom. Seal the bottle with clay around the straw, warm the bottle with your hands and watch the colored liquid rise in the straw as it expands. Cool it down, and the liquid drops. To calibrate, mark the straw at cold, ice water, and warm, tap water. Now you have your own working thermometer. Compare temperatures around your home or classroom. Science you can build and use. What a journey. We've learned about temperature, heat, and the amazing tools we use to measure them. These principles, expansion, resistance, radiation, explain much of the world around us. Notice them in daily life, bridges, toasters, even weather reports. Science is everywhere. Keep asking questions and exploring. Want to learn more? Check out WUNA Educational Services for free lessons and experiments. Keep your curiosity alive and keep learning. Thanks for joining me today. Go out, observe, and maybe invent your own way to measure something. The world needs more scientists like you. Keep exploring and making discoveries.